In lesson 2.3, we're going to look at some properties of functions. And to start off, they have even and oddness of a function. Okay, so we're going to describe functions as being even and or odd. And this is closely related to symmetry, and we've looked at ways to find symmetry among the x-axis and the y-axis and even the origin. So for a function to be even, this means that f of the opposite of x equals f of x. Okay, so in the function, if I change the values of x to their opposites, I will end up with the original function. And if you remember, when we were looking at symmetry, we defined the same thing as having symmetry across the y-axis. All right, so even functions have symmetry over the y-axis. Okay. And if we look down here at example 1, we can see that if I have a point here and I reflect it over the y-axis, I'm going to have symmetry. So in this case, I have an even function. Okay, any point that I pick on one side of the function is going to be reflected across the other side of the function. So this shows us even symmetry. If a function is to be odd, that means that if I take the opposite of the x values, that equals the opposite of the function. And in terms of symmetry, what that means is we actually have symmetry over the origin. So odd functions have symmetry over the origin. And if we look at our examples below, we see in example C, if I were to reflect this point over the origin, okay, I have a reflection. This point over the origin would reflect on here. So in part C, we would say that this is an odd function. If I look at point or example B, and I take a point and I reflect it over the y-axis, I would have a point here, which is not on our function. If I reflect this over the origin, I would have a point down here, which is not on our function. So this first point, or about the y-axis, this shows us that our function is not even. And if I reflect this over the origin, this shows us that our function is not odd. So this would be neither even or odd. In example 2, it says to determine whether each function is even or odd or neither, and also determine if the graph is symmetric with respect to the y-axis, the origin, or neither. All right, so even though we have to determine, they're asking us to determine two different things, they're actually the same thing. So if this is even, I'm going to change my x values to the opposite of x. And rewrite that function. And if I simplify this, I get x squared minus 5, which is what I started with. Okay, so I replaced x with the opposite of x, and I get the same thing. So even is yes. The function is even, okay? And it's basically going to be even, odd, or neither. So since we found that it's even, it's not going to be odd. So in terms of symmetry, we know that this will have symmetry over the y-axis. In part B, I have the function x to the third power minus 1. If I want to test to see if it's even, I'm going to change x to the opposite of x. And when I do x to the opposite of x and cube it, I get negative x to the third power minus 1, which is not the same, like we saw over here. X squared minus 5 matched. This does not match, so it is not even. So to check to see if the function is odd, I'm going to say that negative f of x equals the opposite of x to the third plus 1. So in this case, I'm going to multiply both sides by, or sorry, that was minus 1. I'm going to multiply both sides by negative 1. So if I multiply both sides by negative 1, that gets rid of the negative here. So f of x is going to equal x to the third plus 1. And in that case, they are not equal. So negative f of x, f of negative x does not equal f of x. So this is not odd, or not reflexive about the origin. It's not odd. So this is neither. In the third case, I'm looking for to see if it's even. So I'm going to take 5x, negative x to the third power minus negative x. And if I simplify that, I have negative 5x to the third power plus x. So this is not equal. So this is not even. If I want to check for oddness, I'm going to check to see if f of the opposite of x equals the opposite of f of x. Okay, so we know that the opposite of x is this. Now if I multiply negative 1 times my function, do I get this right here? All right, so if I multiply by negative 1, I get negative 5x to the third power plus 1x, which does equal f of negative x. So in this case, yes, this shows oddness, and it's also, sorry about that, it's also symmetric over the origin. Okay. So just to recap here, if it's even, we change f of x to the opposite of what x equals, and we find out what that is. This does not equal the original function, so it's not even. If I want to find out if it's odd, I need to find the opposite of the function. So the function that I have, I'm going to multiply that by -1. And if that equals the opposite of x, then that would be an odd function. All right, so test for evenness first. If it doesn't work, to test for oddness, take the function, multiply it by -1, and see if that's what you get here. In the next example, we're looking at a function to see where it's increasing and decreasing. And if I look at the function here, we've got some weird things going on. Where is the function increasing? So if I look at what's happening to my y values, in this first part, it's going down. My y values are going lower, and this part, it's going up, and it's going up in this part. So in all of this, my function is increasing. So I'm going to write the interval for my x values of where it's increasing. So increasing functions is happening between -4 to 0. And it's not including -4 because that's actually the point that it's changing direction. Okay, so it's going down, and at -4, it turns the corner and starts to go up. This is where it's increasing. And 4 is kind of like the vertex, so we don't include it in the decreasing or the increasing part. So I start at -4, and I'm going all the way up to +4. Or all the way up, the y values are increasing to +4, but the x value is at 0. So these are the x values where the function is increasing. If I want to find out where it's decreasing, okay, where is it going down? I can see it's going down here, and it's going down here. So we have two parts of the function that it's going down. So it's decreasing. Okay, the y values are going down, but what are the x values that occur when the y values are decreasing? Okay, so we're starting at here. My x value is -6. I'm not going. I'm not going to include -6 because at -6 it hasn't decreased any. That's just our starting point. But it's decreasing from -6 to an x value of -4. And also on this side of the function, my x values are 3 to 6. Okay, it's decreasing from x values 3 to 6. And where it is constant, that means there's no change, kind of like flatlining. And that's happening in this region right here. So it's being constant from 0 to 3. Okay, these are the values where it's staying the same. The y values are staying the same from 0 to 3. All right, so now we're going to look at local maximums and local minimums. Now, maximums and minimums, you can have more than one of them in a given region. Okay, so if I look at this function and it's kind of going down, up, down, up. This right here is showing that there's a maximum here. So in between this range or this domain right here, this is the maximum value of this, kind of like the top of the hill. The minimums would be the bottoms of the hills. Okay, so if we look to see where the maximum is where the point in this area, in this general area right here, is the highest and some lowest points. These are called local maximums and minimums. It's not an absolute maximum or minimum because there are higher points on this graph than this this y value of 2. Okay, this keeps going on forever. So I would say in terms of an absolute maximum for this entire graph, our y values go on forever. So there isn't a total maximum or an absolute maximum, but in this general region here where we're looking at where the function is turning and changing directions, we can find the bottom of the hills and the top of the hills in terms of our maximums and minimum. So in this graph, the local maximum occur at the point 1, 2. That's the only place in here that we really have a top of the hill, at the point 1, 2. The local minimum, and actually if there's more than one, we call that local minima, that's plural. And here we're looking minimum at the bottom of the hills. So I have the point -1, +1, and this point 3, 0. In part C, it says list the intervals on which f is increasing and list the intervals on which f is decreasing. So again, if I look at the parts that are increasing, I'm increasing here and I'm increasing here. Okay. So what are the x values that show these parts here? So I'm increasing between -1 and +1. This is showing an increase here, -1 and +1. And again, we're not including these endpoints. And then I'm including 3 to infinity. Okay, because this is going on forever. I can have x values out here that are going to go up to infinity. So this is part A, B, C. Now I need to list the intervals in which they are decreasing. Okay, so here, and again, I'm reading my graphs from left to right. So all these numbers out here are decreasing in my function. Then it goes up, I'm decreasing again here, and then it goes up again. So I would say that for decreasing, I'm going from the x values way out here, which is -infinity, and my biggest x value in this section is -1. I'm also decreasing in this section, and that would be from 1 to 3. Okay, so we got the increasing sections of the graph and the decreasing sections of the graph. In part D, it's asking us, what is the domain? And if we think about our function, and the domain is the x values, it's saying, okay, what x values do I see on my function? And really, I can have x values anywhere, okay, even way out here, and I would get a y value. So for my domain, my x values are all real numbers. My range are all the y values that I have on my function. Now, if I look at my y values, my lowest y value is 0. I don't have any points that are below the x-axis. Okay? So in this case, I have all y values except for, or such that my y values have to be greater than 0. Y has to be greater than, or it can equal 0. Okay, so it's easy to look at a graph to determine the range and the domain. Okay, so the range is, or sorry, the domain is the x values. And if I were to flatten out all of these points on the x-axis, I could have any x value plugged in to this function, or I can find a point for any x value on this function. If I were to look at my y values for the range and I collapse my function on the y-axis, my lowest y point is at 0. Okay, that's the smallest y point that I have. So all my y values have to be greater than 0. This next example, we are going to do in class. We're going to use a graphing calculator, and actually I want to do this on Desmos. So I'm actually going to do this with you in class, and this part down here I want to save for another day. So we're going to stop at this point and we'll finish this up in class.